Welcome to this video. We will start applying the basic network concepts using the Python NetworkX package. Once again, NetworkX is a package that needs to be installed because it doesn't come pre-installed with Anaconda distribution. For the very first time, we need to pip install NetworkX. Once this process is done, we no longer need this cell, and I've already have it installed on my machine. Next, we're going to import NetworkX, and we usually give it the alias NX. This directive is put here so that the plots of the network show within the notebook. Let's take a look at some of the basic vocabulary using NetworkX. To create a network, we can use the function graph. .nx.graph creates a graph object, which is a synonym to network in NetworkX. There are two kinds of graphs, or networks. Indirect networks, which is the default, and directed network. In indirected networks, the edges are symmetrical. So for instance, if we add three nodes, set using the function addNode, Alice, Bob, and Chuck, if we add an edge in between Alice and Bob, it means there is also an edge in between Bob and Alice. So in a graph, in an indirect network, you can think about this as friendship. If Alice is Bob's friend, it also means that Bob is Alice's friend. We can take a look at the nodes by calling the function nodes, which gives us a view of the nodes. And we can do the same for edges. Now this function nx.draw is pretty useful because it allows us to draw the network within the notebook. That said, this is not the most advanced network plotting tool out there. It does an okay job for small to medium-sized networks. When networks grow in size, there are better tools out there. That said, I'm going to draw the network one, and I'm going to plot it with labels. So as we can see here, we have three nodes, Alice, Bob, and Chuck, and there are two edges here. Let's take an example of directed networks. To create a directed network, we create the network using the digraph function. Everything else is the same. We can add nodes, and we can also add edges. Now, notice here, if we do net2.edges, it's going to grab the edges from Alice to Bob and Bob to Chuck. And those edges are directed, meaning there is no edge from Bob to Alice. You can think about this, for instance, asymmetrical relationship in, for instance, a job position. If Alice supervises Bob and Bob supervises Chuck, those relationships are asymmetrical. It doesn't mean that Bob supervises Alice or Chuck supervises Bob. If we call the function draw, you can see that the edges now have a small arrow here, indicating the direction of the relationship. This also means that we can also add an edge from, for instance, Chuck to Bob, and those will show completely as two different edges. So if I do Chuck to Bob here, you can see that we've got three edges now, and we've got this as double-headed arrow because there are two arrows plotted on top of each other here. Now that's not the same when we have an indirected network. If we add a relationship between Chuck and Bob here, that doesn't change the fact that we only have two edges because those two edges are redundant. And if we plot it, it's exactly the same. Okay. Let's talk about edge weights. Many often the edges themselves carry more information than just the fact that two nodes are connected. For instance, we can have information about the frequency of the interaction, the strength of the relationship, the distance between the two people. Any kind of information can be added as an attribute on the edge itself. So for instance here, we are adding one attribute called weight, and we're saying that the weight of this edge is 2 and the weight of this edge is 1. If I call the function edges, I'm going to see the two edges as in the past, but if I use the option, set the optional parameter data to be true, I'm going to see the attributes here. And in general, it's possible to add more than one attribute. So for instance, let's say we have an attribute called distance here. That's fine too. We have two attributes, weight and distance. And those attributes become important in many algorithms that we will take a look at soon, such as shortest path in between the two nodes. Those weights can be taken into consideration. Let's now visit or revisit the Apollo 13 movie network, which was presented on the slide deck. Let's create the network and let's add the nodes representing the actors here. Next, I'm going to add edges in between the actors. On each edge, I'm going to indicate the movies that the two actors kind of showed in. And this is important here to see that this attribute can be a list, can be any Python object for this case. And that's the case because two actors can show in multiple movies. In this example, I think each pair of actors only showed once, but in general, it's possible to have two actors playing in multiple movies. Now let's draw the network. That's the Apollo 13 movie network. Now we take a look at this network and it's plotted as a figure, a graph, which is usually what we do for small to medium sized network. When networks become larger and larger, it's become harder to plot them on a figure. They will be pretty dense, and we call this network a hairball because there are so many edges in between the nodes. It looks like a hairball. Mathematically, there are two ways to represent a network. From a data structure perspective, we can represent a network either using an adjacency matrix or an adjacency list. An adjacency matrix is basically a matrix which indicates whether edges exist in between the nodes. So you can think about your nodes, that's the Apollo 13 movie networks here, Tom Hanks, Bill Paxton, Gary Sinise, and so on. And so that's node number 0, number 1, number 2, number 3, and number 4. 0 here means there is no link between node 0 and itself. 1 here, it means there is a relationship between node 0 and node 1, right? And that's something we see here. So the adjacency matrix is kind of a compact representation of the network. And this matrix is symmetrical, obviously, because the network itself is indirected. If the network was to be directed, this matrix is not necessarily symmetrical anymore. The adjacency matrix is useful, especially when we want to store the network in a compact form, and also many algorithms under the hood utilizes the adjacency matrix and use some matrix calculations to process the network. The other data structure widely used to represent a network is the adjacency list. And indeed, what we've done here when we did the edges view, that's the adjacency list. It's basically listing the adjacency or the edges in our network. That's another way to represent the network. Once we have a network modeled and represented, we can talk about the network structure. Let's talk about different aspects of the structure. We'll start with cliques. Cliques basically are a subset of nodes that are all completely connected. So for instance, if we have two people, it's a clique of two, right? If somebody is a friend of the other person, Alice is a friend of Bob, then Bob is a friend of Alice. Everybody is a friend of each other. This is a clique. Well, a clique can be of size more than 2. If you have 3 people and all of them are connected, it's a clique. Similarly, for 4 people, if we have 4 persons and each pair of 2 people are connected, it's a clique. In this example here, we want to see each person and the clique they belong to. For instance, you can see that Tom Hanks here belongs to one clique, which is Gary Sinise, Bill Paxton, and Tom Hanks. If we take a look at the network here, You obviously can see this pretty well visualized because it shows as a triangle here in the network. Now people like, for instance, Gary Sinise, they're part of cliques of size 3 and cliques of size 2. Usually cliques of size 2 are not so important. The cliques become important when we're talking about sizes of 3 or more, because those basically represent, densely connected areas or subnetworks. Now cliques represent connectivity in those among different nodes in the network. In general, it's possible to look at whether two nodes are connected and also calculate the shortest path in between these two nodes. So let's take a look at this example here. We're going to use the function shortest path on the network Apollo, and we're going to look for the shortest path between Tom Hanks and Kevin Bacon. And we can see that the shortest path goes through Gary Sinise and then Gary Sinise and Kevin Bacon. Now this algorithm shortest path is very important. It's used in so many applications for routing messages through networks. For instance, we're using the internet. The Internet Routing Protocol uses a version of the shortest path algorithm to route packets through the routers. And in general, there may be multiple shortest paths in between different nodes. And the shortest path algorithm can also make use of the weight information on the edges. If the two nodes are not connected, so in this hypothetical example, I'm adding a node representing myself here. Unfortunately, I haven't played in any movie yet. So if I draw the network here now, I'm going to put labels or with labels equal to true. Let's see. You can see that there is this node here which is completely disconnected from the network. Then I'm trying to calculate the shortest path between this node and, for instance, Tom Hanks. I'm going to get an error here because there is no path exists between these two nodes. This is an opportunity to catch this error. If I wish to do something here, for instance, I can do try, catch, except this error, or any error in general. I can say, well, no path exists. I need to import probably this class, so I'm going just to put a general except here. So this concludes the discussion here. Network X makes it pretty straightforward to represent networks. We create the network, we add the nodes, and then we add the edges. And then it also gives us a slew of different functions to visualize the network, to represent the network as an adjacency matrix or a list, as well as many algorithms to process the structure of the network.